Welcome to the deep dive. Today, we're really getting into the weeds with register transfer logic. It's a fundamental way to describe how information flows and gets processed inside digital systems, especially computers.
Absolutely. If you've ever wondered how your computer actually works at a low level, this is it.
Exactly. And, when state tables get too massive for complex systems, RTL gives us a better handle on things.
It really does.
Yeah.
It's about understanding those core building blocks.
We've gathered some resources that are honestly pretty detailed, almost like study notes for a computer organization exam.
Huh. Yeah. They definitely go deep into RTL and designing things like processor units and ALUs. It's essential stuff.
So our mission today is to really break down these basics. We want to get a solid grip on register transfer logic, how data moves, bus transfers, memory interactions.
And then dive into designing ALUs, accumulators, all those key pieces.
Right. Think of this as really cementing that foundational knowledge. So, okay, let's start with why we even need RTL. What problem does it solve?
Well, like you hinted, digital systems are networks of hardware modules, right? Flip-flops, gates. And for simple sequential circuits, state tables work. They show states, transitions, inputs, outputs.
It's for small stuff.
But imagine trying that for a whole computer. The number of possible states is just astronomical.
Yeah.
Totally impractical.
Right. Completely unmanageable. You'd never be able to list them all.
Exactly. So we need a more modular way to think about it. RTL lets us focus on the flow of information between functional units, registers, counters, arithmetic units.
So we zoom out from individual gates to look at these bigger blocks and how data moves between them.
Precisely. It's about the transfer of binary coded information between registers.
Okay. So what are the key components of this RTL approach? Our sources mention four things.
Yeah, four main aspects. First, the set of registers in the system. And register is a broad term here.
It's not just one thing.
No. It includes things like shift registers, counters, even memory units can be viewed this way. Basically anything that holds binary information.
Got it. Holding places for the zeros and ones. What's second?
Second is the information itself stored in those registers. And again, it's not just numbers.
Right.
It's any binary coded info. Could be numerical data, could be characters like ASCII, instruction codes telling the processor what to do, memory addresses.
Control information, maybe.
Yep, control signals too. It's all just patterns of bits at the end of the day.
Okay. Registers hold the data. Data represents various things. What do we do with it?
That brings us to number 3. The operations performed on the information. These are called micro-operations.
Micro-operations, like small actions.
Exactly. Elementary operations. Things like shifting bits, counting up or down, adding, clearing a register, loading new data.
And these happen quickly.
Yes, a key point, especially for test prep, is that a micro-operation is typically an elementary operation performed in parallel on all the bits of a register during one clock pulse.
Parallel, meaning all bits at once in that single tick of the clock.
Correct. Now, the sources do mention older serial computers, where it might take multiple clock pulses, bit by bit. But for modern parallel systems, it's one clock pulse.
Okay, one pulse per micro-op. What's the fourth component?
The control functions. These are the timing signals and conditions that actually initiate the micro-operations.
Ah, the conductors of the orchestra.
Kind of, yeah. They sequence everything, making sure the right operation happens at the right time based on certain conditions being met.
So registers, information, micro-operations to manipulate it, and control functions to trigger them. How do we write this down systematically?
That's where register transfer language, RTL, comes in. It's a symbolic notation. Think of it like a specific shorthand for describing these hardware actions.
So not quite a programming language, but a way to express these hardware-level operations.
Exactly. A typical RTL statement has a control function part, specifying the when, followed by the micro-operation part, specifying the what.
Like, if condition X is true, then do operation Y.
Precisely. The control function is usually a Boolean expression. If it evaluates to 1, true, the micro-operation listed after the colon happens.
And RTL has symbols for registers and things.
Yes. Registers are usually capital letters, maybe with numbers like R1, R2, or abbreviations hinting at function, MAR for memory address register, PC for program counter, IR for an instruction register.
Giving names to the boxes.
Pretty much. And we need to talk about the bits inside those boxes too.
How do we refer to individual bits in, say, an 8-bit register?
They're numbered. Usually 0 to N1 or sometimes 1 to N. So in an 8-bit register A, you might talk about A0 or A7.
And how are registers drawn or represented?
4 common ways shown in the material. A simple rectangle with a name. Or showing individual cells like little boxes for each bit, maybe with subscripts.
Okay.
Or just numbering the bits along the top of the rectangle. And for bigger registers, like maybe a 16-bit PC, you often see it split into parts, like PCH for the high bits and PCL for the low bits.
Like PC high and PC low.
Exactly. Useful if you need to operate on just half the register, for instance.
Makes sense. And is there a formal way to declare these in RTL?
Yep. There are declaration statements, like declare register A, MBR12, PC16. That sets up an 8-bit A, 12-bit MBR, 16-bit PC.
And subregisters for PCH and PCL.
You can declare those too. Declare subregister PCL, PCH, PCH, etc. 916. Assuming a 1 to 16 numbering, it clearly defines those partitions.
Okay, got the definitions down. Now the core action, transferring information. How's that shown?
With a replacement operator, it looks like a left-pointing arrow.
Ah, the arrow.
So AEB means copy the contents of register B into register A.
And that takes
1 clock cycle in a parallel system. That's fundamental, but also important. The source register, B, doesn't change. The destination, A, gets overwritten. Its old value is lost.
Okay, source unchanged, destination overwritten, 1 clock cycle. What if we only want the transfer to happen sometimes, like conditionally?
That's where the control function comes in. You write the condition first, then a colon, then the transfer, for example. X21, AEB.
What does XT1 mean there?
It's a Boolean condition. Maybe T1 is a timing signal that's high during a certain clock phase, and X means the logical not T of some control signal X. So the transfer A-B only happens if T1 is high, A and D X is low, making the whole expression XT1 true equal to 1.
Ah, so the condition acts like a gate.
Exactly. And in hardware, the source register B's outputs are wired to register A's inputs, but register A has a load control input.
Right.
The control function logic, like an inverter for X and an A and D gate for X ADT, generates a signal that enables that load input only when the condition is true, and it's synchronized with the clock pulse.
So logic gates implement the condition, and that output controls whether A actually loads the data from B on the next clock tick.
You got it.
Now, what if register C needs to get data sometimes from A and other times from B, say T1, CA, and T5, CEB? You can't just wire both A and B to C, can you?
No, that would cause conflicts. You'd have signal contention. The solution is a multiplexer, or MUX.
The data selector.
Right. You'd feed the outputs of A and B into the data inputs of a multiplexer. The control signals, derived from T1 and T5 in this case, would act as the select lines for the MUX.
So the MUX chooses whether A's data or B's data gets passed through.
Exactly. The output of the MUX then goes to the input of register C. And C still needs its load signal activated when T1 is active and A is selected, or T5 is active and B is selected, to actually grab the data.
And for, say, 8-bit registers, you'd need an 8-bit wide MUX.
Or more precisely, 8 2-to-1 multiplexers, one for each bit position, all controlled by the same select logic.
Got it. The MUX routes the chosen source to the destination. Before we move on, the sources listed some basic RTL symbols. Can we quickly recap those?
Sure. Capital letters for registers, the arrow for transfer, subscripts for specific bits like A2, parentheses for register parts like PCH. The colon separates the control function from the micro-op. A comma separates concurrent micro-ops happening at the same time.
Like AEB, BEA, although that needs a temp register usually.
Right. A direct swap like that often implies simultaneous action or temporary storage. And finally, square brackets are used for memory addressing, which we'll get to.
Great summary. Okay, so we can transfer between specific registers, but computers have lots of registers. Connecting every possible pair sounds like a wiring nightmare.
Oh, it would be. Absolutely impractical and expensive. That's why we have bus systems.
A common pathway idea.
Exactly. A bus is a set of common lines, 1 line per bit, usually. Registers share these lines to transfer information, but only one source can transmit onto the bus at any given time.
One talker, potentially many listeners.
Good analogy. Control signals manage who gets to put data on the bus and who gets to listen, read data from the bus.
And how are buses often built? You mentioned multiplexers before.
Multiplexers are key here, too. Imagine you have 4 4-bit registers needing a common bus. You'd use 4 4-to-1 multiplexers.
1 MUX per bit line.
Right. MUX0 gets bit 0 from all 4 registers, MUX1 gets bit 1 from all 4, and so on. 2 shared selection lines would then choose which of the 4 registers gets its data connected via the MUX outputs to the 4 lines of the bus.
So the MUXs select the source register onto the shared bus. Okay, how does main memory fit in? Transferring data between the processor and memory is obviously vital.
Absolutely. Memory transfers involve moving data between main memory M and processor registers. Two basic operations, read and write.
Read is memory to processor.
Yes. Often involves a specific register called the memory data register, MBR, or memory buffer register, MBR. RTL might show as MBR. MM represents the memory system.
And write is the other way.
Correct. Transferring from a register like MBR to memory, MBR.
But memory has addresses. How do we specify where in memory?
Using the square brackets we mentioned earlier, MADRS refers to the specific memory word at that location.
And how is the address itself handled?
Usually with a dedicated memory address register, or AR. The AR holds the address of the memory location we want to access.
Right.
So a read operation, putting data into a data register, DR, would look like DRAAR. This implies the address is already in AR. Memory fetches the data at that location and sends it to Docker.
And a write from, say, register R1?
Would be MAR R1. Data from R1 goes to the memory location pointed to by AR.
So AR holds the where, DR or MBR holds the what's being transferred?
That's the idea. And in a real system, you have address buses and data buses connecting the processor registers to the memory unit. Multiplexers might select which register provides the address and which register receives the data on a read or provides it on a write. Decoders in the memory unit use the address to pinpoint the exact location.
Okay, data movement covered. Now for the fun part, actually doing things with the data. Arithmetic and logic micro-operations, right?
Exactly. Let's start with arithmetic. The basics are addition, subtraction, increment, decrement, and arithmetic shifts, which we'll group with other shifts later.
Increment, decrement seems simple. Just add or subtract one.
Yep. Often done with simple combinational logic or dedicated up-down counter circuits.
What about adding or subtracting the contents of two registers, say A and B?
The RTL for addition is FA plus B. Store the result in F. Hardware-wise, you need registers A, B, and F, and a parallel adder circuit connecting A and B's outputs to F's inputs.
So the RTL statement directly maps to the hardware needed.
Very much so. Like T2, AA plus B. That means when T2 is active, connect A and B to an adder and load the sum back into A, or T5. A plus 1 could use a counter function built into register A.
Got it. What about multiplication and division? Are those single micro-operations?
Usually not. Our sources say they're typically implemented as a sequence of simpler micro-operations, like additions and shifts for multiplication or subtractions and shifts for division, controlled by more complex logic.
Ah, so they're built up from the primitives. Okay, what about logic micro-operations? These work bit by bit, right?
Precisely. They perform bitwise operations. Each bit in register A is operated on with the corresponding bit in register B independently. Common ones are AND or XOR, not complement.
Can you give an example? Maybe XOR?
Sure. F, A, or E. If A is 1010 and B is 1100, then F becomes 0, 1 is 0. Because 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 0 XOR 0 is 0, done for each bit position.
And these are used for OOP.
All sorts of bit manipulation. Selectively setting bits, clearing bits, masking parts of a word, making logical comparisons. Very powerful.
I remember seeing the plus sign used in two different ways in the examples. That could be confusing.
Yes, that's a very important distinction. Context is everything here.
How so?
When plus appears within a micro-operation like A plus B, it always means arithmetic addition.
Okay, inside the action part equals math.
Right. But when plus appears in the control function part, before the colon, like T1 plus T2, it means logical OR.
Ah, so that condition is true if T1 or RT2 is active.
Exactly. The sources sometimes use the explicit symbol for logical OR within microoperations to avoid ambiguity, like in T1 plus T2, A plus B, C, D, A, F. Here, A plus B is arithmetic, DF is logical OR, and T1 plus T2 is the logical OR condition for triggering both.
Got it. Context is key. Plus means different things depending on whether it's in the control part or the operation part.
Okay, last category, shift microoperations, moving bits left or right.
Correct. Shifting register contents. Used for serial data transfer and also crucial parts of multiplication division algorithms. Symbols are usually A SHRL for shift left, SHR for shift right.
So A SHRL, A shifts A left by 1 bit.
Yep, and B, A SHAR B shifts B right by 1 bit.
What happens at the ends? Bits falling off and empty spaces appearing.
Right. The bit shifted out one end is usually lost, unless it's a circular shift. The empty spot created at the other end is filled by a serial input bit. What that input bit is defines the type of shift.
Okay, what are the types?
3 main ones described. Logical, circular, and arithmetic.
Let's go simplest. The serial input is always 0. So shift left fills the rightmost bit with 0. Shift right fills the leftmost bit with 0,
Okay, circular shift.
also called a rotate.
Yep.
The bit shifted out, one end wraps around and becomes the serial input at the other end. Like a shell, A1er means the leftmost bit wraps around to become the new rightmost bit, A1, after a left shift.
Ah, like a loop, an arithmetic shift.
This is usually about shifting right and preserving the sign of a signed number in 2's complement. The find bit, the leftmost bit, is copied into the newly vacated positions to its right. So shifting a negative number right still results in a negative number.
That's important for division by powers of 2 with signed numbers.
Exactly.
Yeah.
The source also showed a generic A, sure, and AE, where E is some external 1-bit serial input for the right shift.
Okay, logical, circular, arithmetic, different ways to handle the ends and the fill-ins. Now we have all these pieces: registers, transfers, buses, memory access, micro-operations. How do they come together in processor logic design?
This is where we build the data path of the CPU. It's about organizing registers and functional units like the ALU and shifter and connecting them, usually with buses, so data can flow between them under the control of those signals we discussed.
How's a typical processor data path organized? The source showed a bus-based example.
Yeah, common structure uses internal buses. The example had, say, 4 registers feeding into 2 multiplexers, MUXA and MUSB.
Selecting the inputs for the ALU.
Exactly. MUXA selects one operand onto bus A, MUXB selects the other onto bus B. These buses feed the Arithmetic Logic Unit, the ALU.
Which performs the actual operation.
Right. The ALU operation itself is chosen by control signals. The result from the ALU then often goes through a shifter.
For those shift operations we just talked about?
Yep. Left, right, or no shift. The shifter's output goes onto an output bus. Let's call it the S bus.
And where does the S bus go?
It connects back to the inputs of all the processor registers. A decoder, controlled by destination select signals, chooses which register gets to load the data from the S bus.
So, source is selected by MUXs, operation by ALU control, optional shift, result routing back to destination register via S bus and decoder.
That's the flow. Plus, the MUXs might also select external data coming in, and the S bus might send data out.
Let's trace an example. How about R1, R2 plus R3? What signals are needed?
Okay, for R1, R2 plus R3, the control unit needs to set MUXA's select lines to choose R2, set MUXB select lines to choose R3, set the ALU function select lines to ADD, set the shifter control for no shift, direct pass-through, and finally, set the decoder's input to select R1, activating its load enable signal.
Wow, that's like 5 or 6 different control signals that have to be set correctly just for one simple addition.
It really highlights the complexity of the control unit's job, doesn't it?
It really does. Is there an alternative to this kind of register file and bus structure? The source mentioned scratchpad memory.
Yes, scratchpad memory is another approach. It's a small, fast, on-chip memory that essentially acts like a register file. It can sometimes be more cost-effective than lots of dedicated registers and complex busing.
How does it differ in operation?
The main difference is how operands get to the ALU. Instead of MUSs selecting register outputs directly, data is typically read from the scratchpad memory into temporary registers, we call A and B first, then fed to the ALU.
So it's more like memory reads before the operation.
Kind of. Let's redo R1, R2 plus R3 using a scratchpad where R1, R2, R3 are just locations, addresses. Say R2 is address 2, R3 is address 3, R1 is address 1.
Okay.
The sequence might be T1. Read R2, mem2 into temp register AT2. Read R3, mem3 into temp register BT3. Perform A plus B in the ALU, and write the result back to R1, mem1.
That seems like more steps. T1, T2, T3 instead of just one control signal pulse.
It can be. There's potential latency reading from the scratchpad sequentially. However, some designs use 2-port memory.
Meaning?
It allows reading 2 different locations from the scratchpad simultaneously in one clock cycle. That helps speed things up by getting both operands at once, closer to the register file model.
Ah, okay, a way to mitigate the delay. The source also talked about an accumulator register. What's that? Sounds like old school calculators.
It has roots there, yeah. An accumulator is a special register used for intermediate results and calculations. In simpler architectures, it's often the implied source for one operand and the implied destination for the result of many ALU operations.
Like a central workbench for calculations.
That's a good way to put it. Instead of specifying 2 source registers and a destination, many instructions might just operate between the accumulator and one other operand, like memory or another register, with the result landing back in the accumulator.
So how would we add R1 and R2 using an accumulator? Let's call it A.
A typical sequence might be T1, clear the accumulator, A, AU neo. T2. Add R1 to the accumulator AAA plus R1, T3. Add R2 to the accumulator AA plus R2. The final sum is now an A.
It seems like instructions could be shorter if they don't need to name the accumulator all the time.
That's a potential advantage, yes. It can lead to more compact instruction encoding. Now, alongside calculations, we need to know about the results. That's where the status register comes in.
Ah, the flags, like carry 0.
Exactly. The status register, or condition code register, holds individual bits, flags, that get set or cleared based on the outcome of ALU operations. Our source focuses on 4 common ones in a 4-bit register, C, Z, S, and V.
Okay, C is carry. What does that track?
Carry C is usually set if an addition results in a carryout from the most significant bit, or if a subtraction requires a borrow, crucial for multi-word arithmetic.
Makes sense. Z is 0.
Yep, Z is set to 1 if the entire result of an ALU operation is 0. All bits are 0. Otherwise, Z is 0. Very useful for checking equality after a subtraction, for instance.
Right, S is signed.
S usually takes the value of the most significant bit, MSB, of the ALU result.
Yeah.
In 2's complement, the MSB indicates the sign, 0, positive, 1, negative. So S tells you the sign of the result.
Got it. And V is overflow. That sounds important for errors.
Very important for signed arithmetic. V, overflow, is set if the result of a signed arithmetic operation is too large or too small to fit in the number of bits available.
Like adding 2 big positive numbers and getting a negative result because it wrapped around.
Exactly that kind of situation.
Yeah.
The source explains it's set if the carry into the MSB position is different from the carry out of the MSB position. Their XOR is 1. For an 8-bit signed number, negative 128 plus 127, adding 100 plus 100 would cause an overflow, setting the V flag.
So these flags give us meta information about the result. How are they used?
Commonly for control flow. Conditional jumps in programs rely heavily on checking these flags. Jump of 0, branch of carry set, etc.
So the program can react to calculation outcomes.
Precisely. And V is used for error detection. The source also gives examples like checking equality, A XOR B, check Z, checking a single bit, A and D with a mask, check Z, or comparing unsigned numbers, A, D, then check C and Z flags.
Okay, Z1 means AB. What about C after AB?
For unsigned AB, if C1, no borrow needed, then AB. If C0, borrow occurred, then AB. Combining C and Z gives you all comparisons.
Very useful. Okay, we keep mentioning the ALU. Let's really dissect it. What is an ALU?
It's the heart of the calculation part of the CPU. A combinational logic circuit that can perform multiple different arithmetic operations, A and D, multiple different logic operations.
A versatile calculation engine.
Right. Which specific operation it performs is chosen by control signals, often called function select lines. With K select lines, you can potentially specify up to 2 K operations.
And how do you go about designing one? The source mentions stages.
A typical approach is 1. Design the arithmetic section. 2. Design the logic section. 3. Combine them efficiently.
Let's start with the arithmetic part. What's the core component?
Usually a parallel adder made by cascading full adders. Remember, a full adder adds 3 bits, 2 input bits plus a carry-in, and produces a sum and a carry-out.
Okay, the ripple carry adder structure. How does that do more than just add?
By cleverly controlling the inputs fed into the parallel adder. Specifically, you manipulate one of the main data inputs, let's call it B, and the initial carry-in SIN to the first stage.
How do you manipulate input B?
The source shows a circuit using selection signals, S0 and S1 maybe, to transform B before it hits the adder. Based on S0, S1, it might pass B straight, pass the complement of B, pass all zeros, or pass all ones.
Ah, so you feed the adder modified data.
Exactly. Combine that with controlling SIN. For A plus B, you pass B and set SIN 0. For A minus B, which is A plus 2's complement of B, you'd pass B, 1's complement, and set SIN 1. The function table in the source is key here, mapping S0, S1, SIN to operations like ADD, SUB, INC, DEC, etc.
Clever. Using one adder structure for many functions just by tweaking the inputs. Now the logic circuit part.
Logic offs are bitwise. Well, you could design a circuit for all 16 possible functions of 2 variables using 4 select lines. The source focuses on a simpler common design for A and D or XOR, not using maybe 2 select lines.
Has that built?
Typically, for each bit position, you have separate gates, A and D or XOR. The outputs of these gates for bit I go into a 4-to-1 multiplexer for bit I. The logic select lines control all these MUXs simultaneously, choosing which logic operations result appears at the output for each bit.
So parallel gates for each function, and MUXs select the desired one.
Yep.
How to combine the arithmetic and logic circuits.
The simple way is another MUX. Feed the arithmetic result and the logic result into a final 2-to-1 MUX. A new select signal, say S2 chooses, S20 gives arithmetic output. S21 gives logic output.
Functional, but maybe not the most efficient. The source hinted at something smarter.
Yes, a more integrated design often reuses the arithmetic adder logic to also perform logic functions. Remember, the sum output of a full adder is f, x, y, u, sin.
Right, XOR of the three inputs.
What if, when we want to do logic, say S21, we force sin to be 0, then the adder's sum output becomes x XOY 0, which is just XOY.
Whoa, so the adder can compute XOR directly if you kill the carry propagation between stages?
Exactly. By designing the logic that generates the inputs to each full adder stage, xi, yi, and the carry z, as functions of the main inputs a, b, and all the select lines, S0, S1, S2, you can make it happen. When S2 is 0, it behaves like the arithmetic circuit. When S21, it forces carries to 0 or manipulates them appropriately and adjusts G, U. So the adder calculates logic functions like XOR or R and D based on S0 and S1.
That's really elegant hardware sharing. Amazing. Okay, after the ALU, there's often a shifter.
Yep, placed at the ALU's output. It might offer functions like pass through, no shift, shift right, shift left, maybe even block the output.
Is it like a shift register?
Could be, using parallel load and then clock pulses to shift.
Oh.
But that's slow. More common is a combinational shifter using multiplexers. It performs the shift or no shift in the same clock cycle as the data passes through, based purely on control signals.
Faster. How's it controlled?
The source describes one using two control variables, H1 and H0 perhaps.
Yeah.
The four combinations select one of the functions, no shift, shift right, shift left, or maybe no operation output disabled.
MUX is again routing bits based on H1, H0. Okay.
Right.
The source then showed a full processor unit example. Can you sketch that out?
Sure. It had about 7 registers, R1, R7, plus a status register. Register outputs fed two MUXs, A and B, selecting ALU inputs. ALU output went through a shifter. Shifter output could go externally or back to the registers via the S-bus, with a decoder choosing the destination register, D field. Control signals F selected the ALU op, H selected the shift.
So MUX A select, MUX B select, ALU function F, shifter function H, destination select D, all controlled externally.
Exactly. The table showed the binary codes for all these fields to execute different microoperations. It also noted how special codes, like VL00, could select external input or no destination.
It really pulls everything together. Finally, there's an accumulator design example, too. How did that look?
It emphasized the accumulator, A, as the central component in a sequential circuit. The combinational logic part takes the current value of A, maybe an external input B, and control signals, P1, P8 in the example, to compute the next state of A.
Focused on the accumulator, what operations did it show?
Things like clear A, load B into A, add B to A, subtract B from A, complement A, unite A with B, or RA with B, XOR A with B. Shift A, right? Notice how A is almost always an operand and the destination.
Implicit accumulator usage.
Right. The design involved cascading stages for each bit, control lines, P1, P8 selecting the operation, and maybe a zero detect circuit. It also mentioned using a decoder to reduce the number of P control lines needed externally, mapping fewer inputs to the required internal signals.
A common design trick to save pins.
Exactly.
Well, this has been an incredibly detailed deep dive. We've gone from why we need RTL through its basic language and components.
Covered transfers between registers, buses, memory access.
Detailed arithmetic, logic, and shift microoperations.
And explored the design of ALUs, processor data paths, scratch pads, accumulators, and status registers. Phew.
It really gives you an appreciation for the fundamental building blocks. You see how these seemingly simple register transfers and microoperations orchestrated correctly lead to complex computation.
It's the foundation upon which everything else is built, really.
Absolutely. So here's a final thought to leave with our listeners. We saw how many control signals were needed just to add 2 registers in that processor example. Considering that, just imagine the sheer scale and complexity of the control signals firing constantly inside a modern CPU to run the sophisticated software we use every day. What does that intricate dance of signals tell us about the challenge of designing not just the data path, but the control unit that directs it all?
That's a great point. The control unit design itself is a whole other fascinating area. Maybe for another time.
Maybe so. Thanks for joining us on this deep dive today.